Hello and welcome to Lifelong Learning with Fulvia. Today's lecture is our last in the three-part lecture series on black holes' gravitational monsters. In part 1, we set the stage for a basic understanding of black holes. In part 2, we talked about stellar mass black holes that form from the gravitational collapse of very massive stars at the end of their lives. Today we talk about supermassive black holes, true gravitational monsters that lurk in the center of most galaxies. In the first part of the lecture, we will talk about supermassive black holes and see that their story begins with the discovery of quasars. We will see that in a somewhat paradoxical way, supermassive black holes are the most powerful gravitational engines in the universe. Then we will spend some time on our very own supermassive black hole at the center of the Milky Way Galaxy called Sagittarius A star. And we'll finish the supermassive black hole portion with the first ever image of a black hole. Then we will briefly cover other topics related to black holes, such as time dilation near a black hole, primordial black holes, Hawking radiation and black hole evaporation, the information paradox, the cosmological black hole era, and finally how the hope of a future theory of quantum gravity will help us better understand black holes. We will very briefly talk about the two most popular approaches to quantum gravity, string theory and loop quantum gravity. Let's briefly review parts 1 and 2. As always, we start with gravity. According to Newton, gravity is an attractive force between masses. It is a universal force, so every particle of matter exerts a gravitational attraction on every other particle. The gravitational attraction is proportional to mass. The greater the mass, the stronger the force. Now, unfortunately, Newton does not give us a cause for this force. Our most complete and current theory of gravity is Einstein's general theory of relativity. Einstein gave us an entirely new way of understanding space, time, and gravity. According to this theory, gravity is a manifestation of the curvature of space, and the space-time curvature is determined by the content of space-time, or by the mass-energy density at that point in space. The greater the density of the body, the greater the curvature, and therefore the greater the gravitational effect. So gravity is not really a force, at least not in the usual sense, but it is a warping or a distortion of space-time. And what we perceive as gravity is just objects moving according to the geometry of space. We said that a gravitational field can be defined as a region of curved space surrounding a massive body which influences the motion and behavior of another body. In part 2, we said that stellar mass black holes are the evolutionary endpoint of very massive stars. During various stages of their lives, stars are in hydrostatic equilibrium, where the inward gravitational collapse is balanced by either the outward radiation pressure generated by nuclear fusion in their cores, or by quantum degeneracy forces in stellar remnants such as white dwarfs and neutron stars. But in very massive stars, gravity wins. Nothing can hold it back, and the core gravitationally collapses into a maximum state of density called a singularity, a point of infinite density and zero volume. Although the stellar remnant has collapsed to a point of zero volume, the black hole has a non-zero boundary called the event horizon. The event horizon is a spherical boundary around the singularity where the escape velocity is equal to the speed of light. This is not a solid surface, but just the calculated distance from the singularity known as the Schwarzschild radius, where the escape velocity is equal to the speed of light. The Schwarzschild radius, and therefore the event horizon, depends on the mass of the black hole. The event horizon is also known as the point of no return, because anything that goes beyond it can never come back out. The central singularity and the surrounding event horizon are the two essential ingredients for a black hole. Since all the mass of the black hole is concentrated in a point, It is an object of extreme density, and therefore it produces an extreme curvature of space from which nothing can escape. Black holes are pretty simple as seen from the outside. They are completely characterized by just three defining properties: mass, the most important property, spin, and charge. These properties are special because they are visible outside the event horizon. All other details of the collapsed object are lost to the black hole itself. So black holes are said to have no hair. In other words, black holes with the same mass, spin, and charge look exactly the same. They are indistinguishable from one another. Now, if a black hole is orbiting another star, it can steal material from that star. As the material swirls faster and faster toward the black hole, the particles collide with one another, gaining heat through friction, forming an extremely hot, glowing disk around the black hole called an accretion disk. Some of the particles will fall into the black hole and be lost forever, while some of them will get ejected along the axis of rotation just outside the event horizon, forming jets of extremely high-speed particles. The last thing we talked about in Part 2 was gravitational waves. The first ever detection of gravitational waves came in September 2015 from the merger of two black holes. This was also the first direct observation of a black hole. All previous observations were indirect observations from a black hole's gravitational influence on a binary companion. In August 2017, the first merger of two neutron stars was detected. This event also produced a gamma-ray burst, which made it the first ever event observed in both gravitational waves and electromagnetic radiation. Just recently, the first detection of a neutron star black hole merger was announced, confirming a decades-old search for a neutron star black hole binary system. Another significant event was the black hole merger detected in May 2019. This is the first ever direct observation of an intermediate mass black hole, with the final black hole weighing in at 142 solar masses. Intermediate mass black holes, are the elusive black holes that fall between stellar black holes and supermassive black holes. The 85 solar mass black hole is also of interest. Based on our current understanding of stellar evolution, black holes between approximately 65 and 120 solar masses cannot form from the collapse of a star. It is likely that this may be the product of a previous merger, indicating that black holes can go through multiple mergers, getting bigger and bigger. And this is the perfect segue into today's lecture: supermassive black holes. Supermassive black holes are giant black holes in the center of large galaxies. It is believed that most galaxies have supermassive black holes in their centers. When we say supermassive, we're talking hundreds of thousands to several billion solar masses. The formation process of supermassive black holes is still not well understood. Some theories suggest that they could form by the merger of many stellar black holes in the early formation of the galaxy. Another possibility is that the supermassive black hole formed first by other processes, such as the collapse of a massive cloud of gas and dust during the early stages of galaxy formation, then the galaxy formed around it. So supermassive black holes might be the seeds of galaxies. There are also other theories out there indicating that this area of research is still very active. Now, supermassive black holes had been unknowingly observed since 1939, long before anyone ever thought to look for them. And unlike stellar black holes that were predicted to exist long before they were actually detected, supermassive black holes were never predicted to exist. The story of their amazing discovery starts with the discovery of quasars. Quasar stands for quasi-stellar radio source. Embedded in the name is the history of these objects. In the 1950s, what would later become known as quasars were identified as radio sources of unknown origin. These were apparently very compact sources, but nobody knew what they were. In the early 1960s, optical telescopes were pointed at these compact sources, and to their surprise, they looked like stars. But when they took a spectrum of these objects, their spectra was telling a very different story. These were like nothing they had ever seen before. Two objects of particular interest were 3C48 and 3C273. In 1962, Martin Schmidt recognized hydrogen absorption lines in 3C273, but they were redshifted by 16%. Shortly after, they discovered that 3C48 was redshifted by an amazing 37%. Now, these numbers tell us that 3C273 is 2 billion light-years away and moving extremely fast. 3C48 is 4.5 billion light-years away and moving even faster. Now, we can see galaxies that far away, but we cannot see individual stars. So here is something more luminous than an entire galaxy, yet it looks like a star. These objects, whatever they are, must radiate an enormous amount of power. Quasars are, in fact, the most luminous objects in the universe. They can be brighter than 100 galaxies, yet smaller than our solar system. So what could they be? Obviously, such amount of power could not come from an ordinary star. The only reasonable explanation was that light must come from a massive, compact, gaseous object that is heated by an enormously powerful engine. That engine turned out to be a giant black hole, but it took some time to recognize that. In the early 1960s, one of the possibilities was the implosion of a supermassive star, 100 million times heavier than our Sun. But the thought of that was utterly ridiculous at the time. After all, black holes were very poorly understood, and the name hadn't even been coined yet. It was becoming clear that astronomers and physicists had to come together and bring general relativity into the picture to try to understand these new discoveries. By the 1970s, it was becoming clear that there was a single central engine responsible for powering all the light, both radio and X-ray. By the early 1980s, astronomers and physicists agreed that the power source must be a giant supermassive black hole in the center of the galaxy. So supermassive black holes are extreme gravitational engines, but that poses somewhat of a paradox. We know that nothing can escape from inside a black hole, and yet they are the power source for the brightest objects in the universe. So how can that be? Well, supermassive black holes feed on their surrounding material, somewhat similar to stellar black holes feeding off of a companion star. But in this case, the supermassive black hole feeds off of the gas and dust in the center of its galaxy. As the material falls and spirals toward the black hole, it gains more and more speed, and the intense friction between streams of material causes the disk to heat up to extremely high temperatures. The gravitational engines work by converting the gravitational potential energy of the infalling material into intense radiation. In other words, supermassive black holes use matter to create light. As matter accelerates toward the event horizon, it emits high-energy electromagnetic radiation. The gravitational engine also produces twin jets of high-energy particles streaming away from the supermassive black hole along the axis of rotation at nearly the speed of light. The jets of particles are accelerated by the intense polar magnetic field and emit radio waves. Let's take a look at the material surrounding a supermassive black hole in this artist's impression. The torus is a donut-shaped ring of gas and dust surrounding the galactic core. This is what the supermassive black hole feeds on. As we get closer and closer to the center, the infalling material from the torus forms the glowing accretion disk. Some of the particles will fall forever into the black hole, while some get ejected away along the axis of rotation, forming jets of highly energetic particles. As we will see in the next few slides, these jets can extend thousands of light years into space. Now, it is important to remember that although the jets appear to be coming from the black hole, they are actually coming from a region close to its event horizon and not from the black hole itself. Here is an image of a giant elliptical galaxy 45 million light-years away. The left is a composite optical and radio view of the galaxy. In the visible light, it appears as a white fuzzy disk of hundreds of billions of stars. The radio image shows a pair of opposite jets emanating from the nucleus and spanning 88,000 light-years. On the right is Hubble's image of the disk of gas and dust that feeds matter into the black hole. We can clearly see the bright central hub which harbors the supermassive black hole. This is a beautiful optical view of Hercules A. In the center is a quite ordinary-looking elliptical galaxy. It is 1,000 times more massive than our Milky Way and harbors a 2.5 billion solar mass supermassive black hole. When viewed in optical light, this is a very familiar view. But what we cannot see in optical light is that Hercules A is one of the brightest radio-emitting objects. And here it is as seen by the Very Large Array Radio Telescope, revealing the optically invisible 1.5 million light-years long jets. And the giant galaxy is just a dot in the center. And here is a beautiful composite view of the image, where we can clearly see that the jets dwarf the visible galaxy from which they emerge. Here's another visible image of a galaxy cluster. It is 2.5 billion light-years away and has a supermassive black hole of about 1 billion solar masses at the center of the bright central galaxy. Here is an X-ray view of the hot intragalactic gases as imaged by the Chandra X-ray Observatory. And here is the same cluster as imaged by the Very Large Array Radio Telescope, in which we clearly see the opposite jets of high-energy particles ejected along the supermassive black hole's axis of rotation. These jets extend approximately 600,000 light-years into space. And here is a beautiful composite image. Quasars are a subgroup of what are known as active galactic nuclei. An AGN is an active center or nucleus of a galaxy with a supermassive black hole that is fueled by a very energetic surrounding accretion disk. AGNs are so luminous that they emit more radiation than all the stars in the entire galaxy. The most powerful AGNs are classified as quasars. Another subgroup are blazars, which are simply quasars with one of their jets pointed toward Earth. Most quasars are very distant, with a peak epoch of activity about 10 billion years ago. So this means that quasars are part of the early universe. Young galaxies, by that we mean galaxies that we see very far away, so we see them as they were several billion years ago, are very active. In other words, their supermassive black holes have a lot of material to feed on, so they have a very bright central nucleus. On the other hand, nearby galaxies, or older galaxies, are much quieter because they have already fed on most of the available material in the galactic center. So although they still have a supermassive black hole, it is not very active and therefore not very bright. As an example of quiet galaxies, our own Milky Way and our closest galactic neighbor Andromeda have pretty inactive nuclei or supermassive black holes. An interesting question is, will their merger in about 4 to 5 billion years reignite a quasar? The closest AGN to us is the radio galaxy Centaurus A. It is about 12.5 million light-years away with a 55 million solar mass supermassive black hole. The image on the left is a composite of the 4 images on the right. Now we've already seen a couple of these, so we will not look at them separately. But in this image also includes the infrared light around the core. This will be one of the targets for the James Webb Space Telescope. This will allow researchers an opportunity to peer deeper through the gas and dust and hopefully understand what is going on in the cores of active galactic nuclei. The record for the most distant known quasar keeps changing, but it is not so much the record that is important as much as what these distant objects can tell us about the formation of galaxies in the early universe. So far, the most distant quasar was reported in January 2021. It is 13.03 billion light-years away. That means we see it as it was over 13 billion years ago, just shortly after galaxies started to form, or just 670 million years after the Big Bang. It is 1,000 times more luminous than our Milky Way, and is powered by one of the earliest known supermassive black holes, weighing in at 1.6 billion solar masses. The presence of such massive black holes so early in the universe's history challenges our current theories of supermassive black hole formation and galaxy growth in the early universe. Black holes created by the first massive stars could not have grown this large in only a few 100 million years. So the question remains about how such massive black holes could have formed so early in cosmic history. It is hoped that the upcoming James Webb Space Telescope will provide new data to give us a better understanding of early cosmic evolution. Let's take a look at just a few significant supermassive black holes. One of the largest supermassive black holes that we know of sits in the center of quasar TON, or TON 618, a little over 10 billion light-years away. It has a mass of 66 billion solar masses. Black holes of this size are sometimes called ultramassive black holes. The first black hole to be directly imaged is M87 star in the center of the giant elliptical galaxy M87. We will talk more about this in a few more slides. The closest billion solar mass black hole is in the center of the beautiful Sombrero Galaxy, only 31 million light-years away. And our closest supermassive black hole is our very own in the center of the Milky Way Galaxy. It is called Sagittarius A star with a mass of 4.1 million solar masses. So let's get to know a little bit more about our very own supermassive black hole. First of all, to find our supermassive black hole, we need to find the center of our Milky Way Galaxy. To do this, we first find the teapot asterism in Sagittarius. Above the spout is the galactic center. But we really can't see anything with the naked eye because of the large amount of gas and dust surrounding the center. Here is a composite image of the galactic center as seen by the Hubble Space Telescope in visible light, Chandra X-ray Observatory in X-ray, and the now retired Spitzer Space Telescope in infrared. The actual center is located in this very bright area. The area is called Sagittarius A. Within Sagittarius A, there is another very compact and bright radio source called Sagittarius A star. This is our very own supermassive black hole. Let's take a look at the history of its discovery. In 1931, Carl Jansky, considered the father of radio astronomy, detected an unknown radio source coming from a location in the direction of the constellation Sagittarius. In 1951, Jack Piddington and Harry Minette discovered a discrete and bright radio source, which 3 years later they described as the probable galactic center. In 1974, Bruce Balick and Robert Brown discovered a bright and very compact source, although at the time they did not know that the source they had discovered was a black hole. In 1982, Robert Brown named the compact source Sagittarius A star because the radio source was very exciting, borrowing the asterisk from quantum mechanics to denote the excited state of an atom. Although by the 1980s it was becoming clear that Sagittarius A star was likely a supermassive black holes, the most compelling evidence comes from studying the motion of stars close to the object. By studying the orbits of stars near the galactic center over many years, astronomers can measure the mass of the object the stars are orbiting. The mass of Sagittarius A star turns out to be 4.1 million solar masses. For this discovery, the German astrophysicist Reinhard Genzel and the American astrophysicist Andrea Ghez were awarded the 2020 Nobel Prize in Physics. Each led separate research groups that explored the center of our Milky Way Galaxy. And both groups found something that is both invisible and heavy, causing stars to swirl around it at extremely high speeds. This is an animation created by Andrea Ghez and her team at UCLA, showing the track of stars around the galactic center. Images from 1995 through 2016 were used to track the stars. Of particular interest is the central yellow track. It is the orbit of the star S2. This is important because it is the first star observed over its full 16-year orbital period. By mapping the orbits of the brightest stars near the center and by applying simple Newtonian gravitation and Kepler's laws, they were able to calculate that the invisible mass had a mass of around 4 million solar masses, squeezed into an area no larger than our solar system. According to our current laws of gravity, there is only one possible candidate for such a mass, a supermassive black hole. The study of S2's orbit around our central supermassive black hole also confirmed the gravitational redshift predicted by Einstein's theory of general relativity, proving once again that Einstein was right. The study was carried out by an international team led by Reinhard Genzel using the European Southern Observatory's Very Large Telescope, and represents the highlight of a 26-year-long observation campaign of S2's orbit. Here is a portion of the orbit as S2 approached its closest point to the supermassive black hole. The closest approach occurred in May 2018. The extremely precise measurements of the light from S2 clearly revealed the gravitational redshift effect. In other words, the very strong gravitational field of the supermassive black hole stretches light to longer wavelengths, or it is shifted toward the red end of the spectrum. And the change in wavelength agrees precisely with predictions by Einstein's general theory of relativity. Now please note that in this impression, the color effect and the size of the objects have been exaggerated for clarity. This is a great visualization of a black hole accretion disk. It simulates how gravity distorts and warps our view of the accretion disk surrounding a black hole. The black hole's extreme gravity alters the path of light emitted by different regions of the disk, producing a misshapen appearance. So the apparent warping of the accretion disk that we see changes as our viewing angle changes. So let's take a look. Here we are viewing the accretion disk head on. And as our view changes to an edgewise view, we get this very strange double-humped appearance. So let's get a better understanding of this rather bizarre appearance. This, of course, is the accretion disk formed by the hot, glowing matter swirling toward the black hole. We notice that on one side, the disk appears brighter than the other side. The effect is due to Doppler beaming. The material moving toward us appears brighter, while the material moving away from us on the other side appears dimmer. Now let's look at the two humps. The top one is light from the far side of the accretion disk, whose light is being gravitationally lensed by the black hole's gravitational field. The bottom one is the light from the underside of the accretion disk. So the gravitational lensing effect produced by the gravitational field of the black hole allows us to see the top and bottom of the far side of the accretion disk as if it were coming from the top and bottom of the black hole. These simulations really help to visualize what is meant by gravity warps the very fabric of space. This is a visualization of two orbiting supermassive black holes. We will see that as they pass in front of each other, the gravitational field of the foreground black hole will warp the light from the background black hole into a sequence of arcs. The simulation contains a larger black hole in red and a smaller one in blue. The different colors simply make it easier to track the light sources. The simulation starts with a rather dull head-on view of the two black holes. Then we get to the edgewise view, and things get a bit more interesting. First, the smaller black hole will pass in front of the larger one, and we will see how its gravitational field distorts the red light from the background black hole. Then the blue black hole will pass behind the red one, and this time the blue light is distorted by the gravitational field of the foreground red black hole. And so let's watch this again as the two black holes orbit each other. Until recently, these visualizations were limited to computer programs. But in 2019, the first ever image of a black hole was released. So let's take a look. This is the groundbreaking first ever image of a black hole and the first visual evidence of their existence. The image is of the relatively nearby supermassive black hole called M87 star, in the center of the huge M87 elliptical galaxy in the Virgo cluster. Its mass is 6.5 billion solar masses. The image was captured by the Event Horizon Telescope, a global network of 8 synchronized radio telescopes around the world. The image shows a bright ring as light bends in the intense gravity of the black hole. This ring of light produces what is known as the shadow of the black hole, or the dark central region silhouetted by the luminous hot material as predicted by Einstein's general relativity. The shadow is about 2.5 times the size of the black hole's event horizon. Analysis of this image has confirmed Einstein's theory of general relativity and has tightened the window on any modifications to the theory. This achievement was also a wonderful convergence of theory and observation. Here we see a simulation of the black hole. A simulation is not a computer animation, but it is an extensive computer program that includes the known laws of physics. In other words, this is what the laws of physics are telling us about the black hole. This is a simulation reconstruction based on the resolution of the Event Horizon Telescope. So this is what we would expect to see if our understanding of black holes is correct. And this is the actual image. It is absolutely amazing. This tells us that our understanding of black holes is on the right track. A question that is often asked is, why is the image brighter on the lower part? The answer is Doppler beaming, which we encountered a few slides ago in the black hole visualization. The black hole is surrounded by a ring of hot gas swirling around the black hole at nearly the speed of light. As the gas moves toward us, it appears brighter, and as it moves away from us, it appears dimmer. Now, from this motion, we can also infer a sense of the black hole's rotation. An M87 star is spinning clockwise as seen from Earth. This groundbreaking image is truly a milestone in our understanding of these mysterious objects. It is the first ever direct image of a black hole, and therefore the first visual evidence of their existence. Together with gravitational wave observations, this marks the beginning of a new era in black hole astrophysics. As we near the end of this series, we briefly take a look at a few very interesting topics related to black holes. Time dilation near a black hole, primordial black holes, Hawking radiation and black hole evaporation, the information paradox, the very distant future cosmological black hole era, and finally quantum gravity, the marriage of quantum mechanics and general relativity. We will very, very briefly talk about two approaches to quantum gravity, string theory and loop quantum gravity. Now, with the exception of gravitational time dilation, which has been proven observationally, everything else we talk about in this section is either a sound scientific theory which has yet to be observationally proven, or simply questions that arise from the study of black holes, for which we do not have any answers yet. Now, we should be pretty comfortable with the idea that a massive body warps or curves the very fabric of space itself, and gravity is a manifestation of that curvature. But what happens to time? After all, time is just one dimension of our four-dimensional space-time continuum. When a massive object warps space, it also warps time. To understand this, let's first recall that according to special relativity, time is not absolute. In other words, time does not flow the same for everyone. The measurement of time depends on the observer. General relativity tells us that gravity affects the flow of time. Specifically, gravity slows down time. In other words, clocks run slower the stronger the gravitational field. Now, this phenomenon has been proven with various experiments both on Earth and in space. And as a side note, our GPS system would not work if the effect of both special and general relativity were not held into account. If you get near a black hole, the effect gets even stronger. A black hole warps space-time so much that at the edge of a black hole, or at the event horizon, time stands still. Suppose we send a probe into our supermassive black hole and tell it to send us back information of what it sees every second. So what does the probe see as it falls in? Well, it passes the event horizon without incident, sending back a report every second according to its clock. But once it passes the event horizon, its fate is set. It eventually crashes into the singularity, and that's the end of the story for the probe. But what do we see? As the probe approaches the black hole, its clock appears to run slower and slower compared to ours. The reports that it sends out every second according to its clock gets less and less frequent according to our clocks, and the signals get more and more redshifted. When the probe finally gets to the event horizon, as we observe it, time essentially stops. Light has redshifted to infinity. And the result is that we never see the probe go into the black hole. Next, we talk about primordial black holes. In our first lecture, we mentioned 4 types of black holes. We've talked quite a lot about stellar and supermassive black holes and a little bit about intermediate mass black holes. So now let's briefly talk about primordial black holes. Primordial black holes are hypothetical black holes that formed shortly after the Big Bang. They usually refer to tiny black holes. For example, if we could squeeze Mount Everest into a black hole, its size would be smaller than an atom. Now we know there is not a natural process today to do this, but could these tiny black holes exist? It is an active area of research, but none have been discovered so far. So why do we think they could exist? Well, so far we've seen that the requirement for any black hole in general is all about density of matter. Specifically, density high enough to generate a gravitational field so strong that nothing can escape. We've seen that in our current universe, to get such high densities, we need either the collapse of very massive stars for stellar black holes, or the enormous mass at the center of galaxies for supermassive black holes. But theoretically, we could get a black hole of any mass as long as we can compress it to high enough density. We do not have these conditions in our current universe, but the very early universe was characterized by extreme pressure, temperature, and density. Under these conditions, simple fluctuations in the density of matter may have resulted in local regions dense enough to undergo gravitational collapse and form black holes. Now, although we often talk about tiny primordial black holes, according to theory, they could have formed with a wide range of masses, ranging from 10 to the minus 8 kilograms to 100,000 solar masses. As a reference, one solar mass, or the mass of our sun, is 2 times 10 to the 30th kilograms. Now, however, theory also predicts that most primordial black holes, those with a mass less than 10 to the 11th kilograms, in other words, much, much less than our sun, would have evaporated by now. But wait a minute. I thought nothing could escape a black hole. What do you mean they evaporate? Well, it is true that according to general relativity, nothing can escape a black hole. But according to quantum mechanics, it's a different story. And that story starts with thermodynamics, specifically the second law of thermodynamics and entropy, or the measure of disorder of a system. The second law of thermodynamics essentially tells us that entropy always increases. Nothing observed in nature or in the universe is immune to the second law of thermodynamics. In 1972, Jacob Bekenstein suggested that black holes must also follow the second law of thermodynamics. Therefore, they must have entropy. Now, initially, Stephen Hawking, one of the greatest physicists of the late 20th century, did not agree with Bekenstein. But after applying the ideas of quantum mechanics to black holes, he not only agreed with Bekenstein, but he found a surprising result. If black holes have entropy, they must have temperature. And if they have temperature, then they must radiate. This radiation from black holes is appropriately called Hawking radiation. So Hawking found that when you apply quantum mechanics to the physics in the vicinity of a black hole, the black hole seems to emit particles. So how can that be? Well, let's start with the quantum mechanical concept of virtual particles. According to the principles of quantum mechanics, empty space is teeming with virtual particles popping in and out of existence. Quantum mechanics allows pairs of virtual particles and antiparticles to borrow energy from the vacuum of empty space and spontaneously appear, then very quickly annihilate each other. This is what is meant by quantum fluctuations. So the particles appear seemingly out of nothing and then quickly annihilate and disappear. This is the static version of what we just saw. So let's see how we get from here to Hawking radiation. Here we see sets of virtual particles popping in and out around, but not too close to the event horizon. So they form, then quickly annihilate each other. But if the particle pairs form very close to the event horizon, one of the particles can fall into the black hole while the other remains outside and escapes. From the point of view of an outside observer, the outgoing particle appears as radiation coming from the black hole. In Stephen Hawking's words, black holes ain't so black. So what do we mean by black hole evaporation? Virtual particles can become real particles if they receive a boost of energy from a surrounding energy field. The escaping virtual particles near the event horizon receive energy from the gravitational field and become real particles. But that energy must come from somewhere. It is the black hole that gives up some of its gravitational energy, and by doing so, it loses some of its mass to give energy to the stream of particles, and it slowly evaporates. The evaporation rate of a black hole depends on its mass. Specifically, it is inversely proportional. So the greater the mass of a black hole, the slower it will evaporate. For example, a 2 solar mass black hole would take 10 to the 67 years to evaporate. As a reference, our universe is on the order of 10 to the 9 years old. So black hole evaporation is an exceedingly slow process. But for very small primordial black holes with masses much, much less than our own sun, they would have already evaporated by now. Another interesting fact about black hole evaporation is that as the black hole evaporates, obviously its mass decreases. So since the evaporation rate is inversely proportional to mass, the evaporation rate increases in time. So as the black hole loses more and more mass and gets smaller and smaller, the evaporation grows faster and faster, until finally, when it has shrunk to less than the size of an atom, the black hole explodes violently in just a fraction of a second in a burst of high energy radiation. Now, as I mentioned in the beginning of this section, Hawking radiation and black hole evaporation are based on very sound theory, but they have not been observed yet. Another consequence of Hawking radiation is what is known as the information paradox. We start with asking the question, what happens to all the information that goes into a black hole? Is it really lost forever? Quantum mechanics tells us that the total amount of information in the universe must be conserved. When an object falls into a black hole, it seems as though all that information becomes irretrievably lost. But that doesn't really break any laws of physics because although the information is out of sight, it may still exist inside the black hole. So the laws of physics remain intact. But when you account for Hawking radiation, it's another story. As we saw, Hawking radiation causes the black hole to evaporate. The radiation is random and contains none of the information about the original content of the black hole. In other words, Hawking radiation does not depend at all on what the black hole is made of. Eventually, the black hole must completely evaporate, leaving no clue as to what fell into it in the first place. So what happens to all the information that has fallen into the black hole? This is the information paradox, and we still do not have a good explanation for it. Now, fortunately, every paradox in science is an opportunity for new discovery. A deeper understanding of general relativity and quantum mechanics must resolve this paradox. And the answer to this puzzle could be the foundation of a future theory of quantum gravity. But before we talk about quantum gravity, I'd like to cover one more topic: the black hole era. This is a possible future era of our universe, assuming an indefinitely expanding universe and with our current cosmological constant, also known as dark energy. Let's see the various eras in a timeline. The timescale is in years after the Big Bang, and please note that it is not to scale. Star formation started around 1.5 million years after the Big Bang, entering into the stelliferous era. At only about 14 billion years old, our universe is currently in the stelliferous era. Eventually, around 100 trillion years, the supply of gas needed for star formation will be exhausted, and all that will be left are the stellar degenerate remnants such as white dwarfs, neutron stars, and black holes. This is known as the degenerate era. And this era will last until the degenerate remnants finally decay, leaving behind only black holes to dominate the universe. This is the black hole era. But black holes will slowly evaporate via Hawking radiation. And after all the black holes have evaporated by around the 10 to the 100 year mark, known as a googol, we enter the dark era. The universe will be nearly empty, with only low-energy photons, neutrinos, electrons, and positrons flying around and hardly ever encountering each other. At this point, a possible scenario is that the universe will be in such a low-energy state that it will approach absolute zero. This is what is known as heat death, or the big chill, or the big freeze. Now, please remember, this is only a possible scenario. We don't really know what the extremely distant future of the universe will be like. And so we come to quantum gravity, the holy grail of physics. Quantum gravity attempts to merge the two great theories of the 20th century, general relativity and quantum mechanics. As we know, general relativity is Einstein's description of gravity. This theory is the foundation of modern cosmology, astrophysics, gravitational waves, and of course, black holes. Quantum mechanics gave us the standard model of particle physics, known simply as the Standard Model. This is a complete mathematical framework that describes all the fundamental particles of nature and their interactions through three well-described forces of nature. Both of these theories are extremely successful on their own and have been proven right over and over again. The problem is they are incompatible with each other. General relativity deals with the very massive, and quantum mechanics with the very small. And when we try to combine the two, we get infinities. So where in nature do we find both the very, very massive and the very, very small? The answer is in the center of a black hole, at the black hole singularity. Recall that a gravitational singularity forms when a very large mass is squeezed into a point of zero volume, which gives us an infinite density. Now, while black holes do exist in nature, and singularities exist mathematically, points of zero volume and infinite densities cannot really exist in nature. John Wheeler, whom we've already seen a few times throughout these lectures, was one of the pioneers of quantum gravity. His interest began with the quest to understand the final state of a gravitational implosion. According to Wheeler, that understanding would require the understanding of the fiery marriage of general relativity and quantum mechanics. It became clear that to explain singularities would require new physics. This new physics would attempt to explain not only black hole singularities, but also the cosmological singularity at the Big Bang. So far, we have two different approaches to quantum gravity, and they are both still highly speculative. One is string theory, and the other is loop quantum gravity. We start very briefly with string theory. String theory is a theoretical attempt to quantize gravity, and then bring it into the fold and framework of the Standard Model, and finally unify all four fundamental forces into a single unified theory, or a theory of everything. Now, string theory did not actually start out as a theory of everything. It started out in the late 1960s as a candidate for the strong nuclear force, but eventually losing out to quantum chromodynamics. However, in 1974, it was discovered that the equations of string theory predicted the existence of the graviton. The graviton is a hypothetical quantum of gravity. In other words, it is the yet-to-be-discovered mediating particle of the gravitational force. This result turned string theory into a possible theory of quantum gravity. So the basic idea of string theory is that it replaces the zero-dimensional point-like particles of the Standard Model with one-dimensional strings. Essentially, the different fundamental particles, such as quarks, electrons, and the hypothetical graviton, are simply just different vibrational modes of a single fundamental string. The math of string theory is extremely complex, and an initial problem was that there were a lot of mathematical inconsistencies. Eventually, they found that by increasing the number of spatial dimensions, the mathematical difficulties became better behaved. So they kept adding more and more dimensions to make the math work. M-theory, the current all-encompassing unified string theory, has 11 dimensions. Now, we are familiar with our 3 dimensions of space and 1 of time, but what about the other 7 dimensions? What do all these dimensions even mean? Well, string theorists will tell us that we cannot perceive the extra dimensions because they are extremely small and curled up or compactified beyond our sensory perception. Basically, they're saying these dimensions are there, trust us, we just can't see them. So let's take a look at the other approach, loop quantum gravity. Unlike string theory that attempts to unify all the fundamental forces of nature, loop quantum gravity is strictly a theory of quantum gravity. It relies on general relativity and attempts to quantize the gravitational field. So it mainly focuses on the quantum properties of space, time, and gravity. In loop quantum gravity, space-time is viewed as composed of finite loops woven into an extremely fine fabric or network. The loops themselves are not in space, but the loops are space. They are space because they are the quantum excitation of the gravitational field, which is the physical space. Now, because loops are space, it makes no sense to think about a loop being displaced by an amount of space. Instead, the location of one loop relative to another is determined only by their intersection. Space is therefore described by a net of intersecting loops. There is no location of the net. In other words, the net is not in space, but there is only location on the net, and the net is space. Loop quantum gravity changes the way we think about the structure of space. Space is not smooth at its original scale. Instead, it has a granular structure. So space is not a continuum. It is formed by discrete quanta of space. Let's summarize the two approaches. String theory aspires to be a theory of everything, one that accounts for all the known forces of nature, including gravity. Loop quantum gravity is strictly a theory of quantum gravity, quantum space, and quantum time. String theory attempts to bring gravity into the framework of the Standard Model. In other words, it treats gravity as just another force. Loop quantum gravity draws its inspiration from general relativity, so it retains Einstein's ideas of space and time and then adds quantum features to it. String theory simply assumes a space-time background, but brings all the four forces together. Loop quantum gravity focuses on space and time and ignores the other forces. So in the end, string theory quantizes gravity and treats it simply as a force, bringing it into the quantum mechanical framework, and loop quantum gravity quantizes space itself, changing how we view the fundamental structure of space and time. So where does this leave us? What these theories show us is that we have two main directions of thinking about the unification of gravity and quantum mechanics. String theory is motivated by the heritage of the Standard Model and attempts to bring gravity into that framework by considering gravity as just another force. Loop quantum gravity continues the Einstein tradition of considering gravity as a property of spacetime and attempts to quantize space and time within the geometric framework. Both of these theories are still very speculative, and neither one is yet fully well developed. One or the other could be right, or both could be wrong, or each could just be a piece of a final theory. In any case, the development of quantum gravity offers a fascinating glimpse of the fundamental structure of nature. Now, as we wrap up this series, we've seen that black holes are some of the most fascinating and mysterious objects in the universe. So let's summarize what we've learned about them throughout these 3 lectures. First and foremost, a black hole is gravity at its most extreme. We can define a black hole as a region of space where matter is compressed to such high density and the gravitational field is so strong that nothing can escape, not even light. The existence of black holes was predicted by Einstein's general theory of relativity. According to general relativity, gravity is the manifestation of the curvature of space generated by mass and energy. The greater the mass density, the greater the gravitational field. Therefore, the requirement for a black hole is a mass density high enough to generate such an extreme gravitational field from which nothing can escape. There are 4 types of black holes. They differ by mass and the manner in which they achieve the required density. The best understood are stellar black holes. They form by the gravitational collapse of very massive stars at the end of their lives. Intermediate mass black holes can form by the merger of 2 stellar black holes. Supermassive black holes are found in the center of most galaxies, although their formation is still not well understood. And primordial black holes. Although not yet observed, they may have formed shortly after the Big Bang when the universe was characterized by extreme densities. How do we know black holes really exist? We can detect black holes indirectly by their gravitational influence on other bodies. For stellar black holes in a binary star system, we can detect the wobble of the Doppler shift of the orbiting companion star. As the black hole and the star orbit each other, the black hole can steal material from its companion, and as the material falls and spirals toward the black hole, it forms a glowing disk of very hot matter which can be detected. As the material spirals closer and closer to the black hole, some of it falls in, never to escape, but some of it gets ejected away along the axis of rotation, forming jets of high-energy particles, which also can be detected. Many supermassive black holes are detected as active galactic nuclei, or quasars. As supermassive black holes feed on the material in the center of galaxies, they form extremely bright accretion disks and extremely powerful jets that can extend thousands of light years into space. The supermassive black hole in our own galaxy was conclusively detected by the motion of stars near the center of the Milky Way. The only possible explanation for their orbital motion is that there is an invisible mass of around 4.1 million solar masses squeezed into a very small area. Only a supermassive black hole can provide such an explanation. And just recently, we also have direct observational evidence of their existence. The first was the detection of gravitational waves from the merger of two black holes. Whereas the indirect evidence comes from electromagnetic radiation from material outside the black hole, gravitational waves come directly from the black holes themselves. Since their first detection in 2015, many stellar black holes have been detected along with the first intermediate mass black hole. The second direct observation method was the first ever image of a black hole in 2019. This is the image of the supermassive black hole in the center of the giant elliptical galaxy M87. Now, all black holes have two essential ingredients: the event horizon, a spherical boundary beyond which nothing can escape, and a singularity at its center, where all the mass of the black hole is concentrated into a mathematical point of zero volume and infinite density. However, when we take a deeper look at these two ingredients, we realize that general relativity doesn't give us a full picture. Stephen Hawking found that by applying quantum mechanical principles near the event horizon, black holes give off a very dim radiation known as Hawking radiation. A surprising consequence of Hawking radiation is that eventually black holes will evaporate in time. Now, it must be said that Hawking radiation has not been detected yet. Then we have the mysterious singularity. Although general relativity tells us that black holes must have a singularity, it cannot explain the singularity itself. When we try to explain the singularity with our two extremely successful laws of physics, quantum mechanics, the physics of the very, very small, and general relativity, the physics of the very, very massive, we find that they break down and cannot give us an explanation. So we need new physics, or the merger of quantum mechanics and general relativity into a single law of quantum gravity. The two most popular approaches are string theory and loop quantum gravity, but these theories are still both highly speculative and not yet well developed. We don't know yet what surprises a future theory of quantum gravity may bring us, and we might find that black holes have even more exciting features beyond our current imagination. This ends our series on black holes' gravitational monsters. I hope you've enjoyed learning a little bit about these fascinating and mysterious objects. And as always, thank you for watching.